Okay, so this is part 2 of animation for the Industrial Technology Multimedia syllabus. So what we're going to be talking about today is 3D animation. Last lesson we looked at 2D animation. And 2D animation is all about flat images, which is fine. 3D animation though gives us a lot more freedom because it really brings us one step closer to live action video. So there's always that fourth wall diorama sort of idea with 2D animation, and it can be really hard to take your camera like from here and move it around to here without drawing your character in that different angle and those transitionary sort of frames. It can be very difficult to do. So often when you've got 2D animation, you've kind of got this like weird flip where you've got a character facing one way and then the next frame you skip that way, and it kind of looks like paper cutouts and dolls. So 3D animation, as soon as we could like get it working, we kind of moved towards that because it allows us to do things that are much more like conventional filmmaking. So with 3D animation, the main difference is that a 3D animated project usually has characters that have a mesh with the skin over the top of them, as opposed to just what's drawn on screen. So if you've got a character, you have a mesh, you rig that character, so you put like a skeleton inside that mesh, so that 3D shape, and then you can move those points on that skeleton and it warps the skin that's on the outside of it. So, for example, when we 3D model, we can use a sculpting tool or a sculpting program. I'm trying to think of some sculpting programs. I've got one on my laptop. Okay, so ZBrush or ZBrush, depending on what country you're in, is a sculpting program, and it's based on the idea of kind of model making and sculpting out of clay. So what you do is you create three-dimensional geometric data, which gives itself a mesh. So it uses Cartesian coordinates, which you don't really need to know about, and it's stored on the computer, those calculations. And so basically you get this sort of geometric squares, and then they get warped to be different three-dimensional points, and then it gets filled in with a solid shape called a polygon. So you've probably heard about polygons before if you're 30 years old like me and you were playing on the original PlayStation or Nintendo 64, because they used to talk about the amount of polygons that you could get on screen at a time, and that's the complexity of the model. Now we've reached the point, so a low polygon model is going to look like one of those early 3D games like Virtua Fighter, where everything's kind of really blocky and doesn't look that great in retrospect. And now we move on to something that's much smoother, higher polygon models, and irrelevant really at this point. So we use mainly high polygon models now that have a lot of detail, and we put a skin over the top of it, and that works to create a 3D rendered graphic. So why that's good is we've got our 3D model in there, and then we can take a camera and we can move it completely around that 3D model, or we can turn our 3D character and it still works in the space. So it provides us with a lot more freedom to really speed things up once we've got everything rigged and moving. And it can create really beautiful, realistic animation if you put in the time to do it. It can be very difficult to do. It's incredibly processor intensive. If you want to do it properly, it'll chug your computer down real slow. I've had Year 12 students working on 3D animations before where it would literally render 1 frame per hour on their laptops. So when you're thinking about a 3D animation, then I think he was doing 30 frames per second, so that was a second every day. He was doing a minute. It took him 2 months to render his final video. Horrible. Okay, so how do we get around that? Well, there are server farms, which are large areas of powerful computers that you can send things to, and it will use that processing power, but all of that costs money. Big studios have their own server farms. Let's move on. So when I'm talking about modeling, we start off with what's called a wireframe. So that's a visual representation of a 3D object on a computer. You specify each edge of the polygon on your object, and it creates kind of like this wiry look, kind of like our 90s idea of the future computers, so like, you know, where it's like green and glowing. I've got an example of a wireframe here. And that's on page 58 if you're following along. So wireframes are pretty fast to calculate. They don't use up that much rendering power. They don't look great. It's only after we mesh and skin them that they start to look interesting. We add certain things like hair, which can flow in the wind, all of that sort of stuff. And that's when it starts becoming more processor intensive. So that's rendering. So rendering is when we start putting our textures on. So we start making things look the way that we want to do that. And the way that a texture works is it's a flat 2D file that gets wrapped around your mesh. So if you've ever seen a texture file for a video game, it often looks a little bit weird because they've kind of stretched the face out. So they've pulled it out and it can look almost comical. But when it gets wrapped around the face, it starts to look realistic. So we can use our wireframes to work out our data of our movement because we don't necessarily need to see the rendered skin on our animation. We can still get realistic animation through a wireframe. Once we've got our animation in, we can do a proper render with everything on top, and then we can see the way that the lights we've played will interact and bounce off our character. We can put in, you know, particles for the hair to get it to flow, wind, all that sort of stuff in. It becomes much more complex. The more complex it is, the more processor power it uses, and it all goes on like that. So rendering is, in this context, rendering is basically coming up with your final file and the final way that a 3D animation can look. But it's not, although rendering shows our final image file, when we talk about rendering in terms of animation and stuff, often we're talking about taking a working file to a final file, and that's not necessarily always the way with 3D animation, because rendering into a file that you can see all the skins and the mesh and everything on may not be changing it into a final file. So with that, you might be just wanting to see what your final image will look like on screen. So you might just render a small section of it, and that can be compared to in After Effects when you kind of load the 2D file up slightly just so you can see it playing back in real time with sound and all of that sort of stuff, okay? So there is an important caveat that I'd like to talk about compared to my previous video. You can render a file just so it plays and shows you a final version of something. It doesn't need to change it into a completely uneditable final file. All right, good. So 3D animation, we then want to talk about morphing again and warping again. So morphing is changing from one image to another image again. Warping is pretty much doing the same thing again. So morphing and warping, changing from one image to another image or distorting it in some way. You can come up with some much more interesting things when you're talking about effects in 3D, please. You can talk about any number of CGI elements. But really, we should also talk about motion capture. Okay, so motion capture is really getting, if you get asked to talk about a new and emerging design, motion capture in 2019, it's hitting the last few years where you can still talk about it as an emerging technology, because it's been around for at least like effectively in 3D animation for like 25 to 30 years now, so it's like old, right? The idea with motion capture is that there are a number of points on a performer's body, whether that performer is a human or something else, it doesn't matter, and then we take those points of the body and we translate over that to a 3D skeleton. Okay, so a skeleton roughly the shape of the animal that we want to have. So if I've got a dot for the motion tracker on my head here, and my head moves, the skeleton will move in the 3D animation program. What we can do then is we can rig that skeleton to a mesh of a 3D character, and then my movements will translate to the movements of those points on the 3D character. So you can use programs like Blender, you can use programs like Maya, and I'm sure there's a whole bunch of other more industry-specific ones, you know, ones that aren't free to students. And the idea is that the camera motion of the person is captured in the 3D model. Now, why is this beneficial? Because it's really hard to animate something realistically in 3D. So we can get a 2D walking motion pretty easily by just doing a walk cycle. But we're only doing it on one plane. Well, we're only doing it sort of along this way, maybe a little bit up. But we never have to sort of view it around from the back or pan around it. So as long as it looks good from the direction that the camera is in, it's pretty much going to be fine. With 3D animation though, it needs to look realistic from every angle. Now, if you've ever tried to stack two shapes on top of each other in 3D, you'll know this idea where it can look really good from one angle. It could be like a circle of a cylinder with a cone on top. It looks perfect from this angle. You pan the camera around and all of a sudden you realize that they're in completely different spots. 3D is hard because you add in that third dimension that's not there, that Z, that depth factor, and it can completely blow out your idea because a computer is a 2D representation. So a 2D representation of 3D space is always going to be difficult to show. So what this motion capture idea does is it lets us take out all of that difficult movement and we can map it to a person's movement or an animal's movement or whatever we decide to motion track. That can make things work really well. So the advantages of that, complex animation can be done really easily. The disadvantages of that, you need the specific hardware and special software programs. It can be incredibly expensive. The hardware especially is very expensive. Now there are a bunch of startup companies at the moment looking to make motion capture software more affordable. But at the moment, it's not quite there. It's really in the beta stages. So in 2019, motion capture is still very expensive. Also, you can't have movement that ignores the laws of physics, okay? You just can't. I mean, you can have a character jump up in the middle of the air and like Matrix style, but that would involve wires and then you're doing practical effects on top of everything else and it can just become very, very complicated. The idea is that you're replicating real movement, so to replicate real movement, it makes it quite hard to replicate unreal movement. I don't know. Anyway, it can also be complicated if the animated character that you're trying to make doesn't have the proportions of a human. So, or whatever it is that you're capturing. So, if a cartoon character has large oversized hands, for example, and I'm moving my hands around like I do all the time, if my hands are bigger, I can just clip them through my head accidentally. So that's something that I've got to be really careful about. If I start having a character that's 30 feet tall with massive legs, things aren't going to be as human-like in their movement anymore, and that can be problematic. So do we have our character start wearing stilts? Maybe, but then the knee joints won't be right. Motion capture is really good for human-shaped objects if you're motion capturing a human. Okay, so those are some things, some disadvantages of it. Moving on to our final thing for this lesson, virtual reality. So I'm going to break virtual reality into two things, virtual reality and augmented reality. Augmented reality is not in the syllabus, but is worthwhile talking about. Virtual reality is the complete immersion in a virtual world. So we usually use some kind of VR goggle to do that. So you've got your Oculus, your Vive, PSVR, Google Cardboard, if you really want to like talk low budget, the Samsung VR, something like that. And the idea is that there is a suspension of disbelief because our outside stimuli are blocked off. So we can't see outside of those goggles. A lot of the time we can't hear outside of the headphones that are on. Our sense of touch can often be changed through the use of controllers. So there'll be touch-based controllers where you'll press triggers and it'll make your virtual hands on screen do certain things. So we feel like we're in a different world. There are virtual reality treadmills where if you walk on the treadmill, it makes you go forward in the game. The whole idea is about presenting a reality that is completely separate from our own. So the goal is to create an immersive world. The screen is basically mounted to your face. You look one way, the screen moves with you. The main difference then between virtual reality and augmented reality is augmented reality overlays graphics onto your view, onto the real world. So we see a camera view or a realistic view in the case of Google Glasses, which was a failed experiment because the technology wasn't there yet, where you can see real life and there's an overlay or a HUD, a heads-up display on there, which gives you further information about something or can create some kind of picture that makes things more interesting. Probably the most famous example of that would be to do with phones and Pokemon Go. So that's a video game where you walk around in real life. When you catch a Pokemon up, you hold your phone up, you can see the world behind you with the Pokemon sitting on front of it on your camera screen. Of course, Pokemon's not there in real life. It's an augmented reality added to the reality on front. A virtual reality version of that would be where you yourself felt completely in the Pokemon world. So that's the difference between the two of those. So the way a VR headset works is you send two versions of a display, one into each eye. So if you've only got one eye, you're out of luck for VR for the most part. So they're slightly offset. So they show two different versions of it, and when they go and move together into our eyes create a 3D-esque version of that. So these lenses focus to create stereoscopic 3D images, so images that appear 3D to us with depth of field, so things are in focus, things are out of focus. So one way to make things better is to work with 360 videos that go the entire way around, because we can lose our immersion when we hit the edge of a 180-degree video. So if you look into something amazing, all of a sudden you see a black screen over there, you're lost. The most important thing for VR is that we want to be immersed in it. We also need to use a high frame rate. So although we can get away with 12 frames a second for movement, if we had that in VR, it introduces latency. So remember that delay, and with that delay can create feelings of motion sickness. It's one of the biggest problems with VR at the moment. People feel like they're going to throw up when they're viewing it. And that's one of the biggest stumbling blocks in actually moving VR into it. So we really want to do 120 frames per second plus. We also need really high resolution, because the lower quality the image, the less immersive it is, because we don't want to view it as a picture on a screen. We want to view it in real life. So real life is not 4K. Real life is, well, there is no resolution to real life. It's real life. The less detailed our image is, the more likely we are to see it as something that's not important, okay? So we head track, and that moves things to move around. We do that through a gyroscope, an accelerometer, and a magnetometer. We don't need to talk about it. Some use LEDs dotted around the headset, which connect into a camera around the room. The Oculus Quest, which came out 3 or 4 months ago, has little cameras built into it, which creates a constant filming of the environment. When it moves on screen, it moves where you are around the room. You set up your own sort of play area. There's also other existing headsets which set up cameras in the room, which constantly track where the VR headset is in relation to it. It needs to have as low latency as possible. If you move, it needs to be less than 50 milliseconds before it moves on screen. Otherwise, you'll get a delay, you'll feel sick, won't be very good, okay? So what do we use them for? We use them for simulations, first off. So a good example of that is riding on a roller coaster while you sit on a chair, okay? So using VR, you can get that feeling of moving up and down in a roller coaster in a movie. Flight simulators are excellent in VR. Just really for immersing yourself in a game. First-person games work really well in VR. As well, we can use them for walkthroughs of building sites and architectural ideas for visiting museums, things like that. So it can be used for rides and events in theme parks at the moment. So I've seen some VR roller coasters where you put on the VR headset, puts you through the roller coaster, but you feel like you're on a different planet or something or other. Google Street View and Google Maps can be used with VR to create movements through different countries. Real estate, so SketchUp is used extensively to have VR walkthroughs and navigable scenes. So that's the idea where you can actually walk through an existing part of a country or through a house or something like that. That tackles everything that's in the syllabus. Currently, since 2008, in the last 11 years, we've really moved towards a sort of gaming, realistic video idea of it. VR is at the moment either potentially going to take off into mass market or fade into obscurity. We'll see what happens. There's still a lot of problems with it, but if you were to talk about emerging technology, VR is a really good one to talk about. You could also talk about augmented reality. Just make sure you don't mix up the two. Virtual reality is full immersion. Augmented reality is an overlay or a HUD on real life. So that is animation, and we're getting through it. I think there's maybe about 2 or 3 more videos to go. So great work.